Welcome to video 2. So I want to talk this time about statistical techniques and the basic ideas of how words relate to each other, and we can try to understand meaning. The background image is actually from state-of-the-art techniques, as in word embeddings. This is the canonical example that you can do math, if you will, because different directions have different meanings. But before we had all this, it was much simpler, and so we're going to talk about that first. In general, we look at what is the context of a word. So that would be all of the words that appear next to it. So once again, in state-of-the-art techniques, we consider a much bigger context window, if you will. We're going to talk in this lesson about n-grams, which are where we look at only sequences of 2 words in a row, 3 words, much, much smaller. But word embeddings are based on kind of larger contexts like this. Now, in this case, the word banking here is the financial term. But if we were talking about a riverbank, you would see a much different context. And so by the words that are surrounding it in a sentence, that's how AI models, natural language processing models, can figure out which meaning is intended. One last thought about word embeddings. So with word embeddings, you can do things like this. Usually word embeddings are 1,000 or more dimensions. Here we've reduced it just to 2 dimensions so that we can actually plot it. You can't plot something that's 1,000 dimensions. You can see we're actually covering a little over half of the variance, so we're missing some detail. But in general, you can see the words that are similar are that you find them closer together in clusters. Here you can see the animals, the colors, and the countries all are relatively close and spaced out. And if we looked in the high dimensional space, I'm sure you'd see much more nuance even between the different types of animals, but some of that you can capture here. Okay, so again, this is more state of the art. Now we're going to look at a really what seems like simplistic mechanism, but it actually turns out to be helpful in a lot of cases, things like spell checkers, things like that. So here we are in our Python notebook for this module, and I wanted to call out some of the Python libraries that we're using. So NLTK, Natural Language Toolkit, this probably gets a little more usage in the academic world, but it's helpful. It does a lot of really nice things for us. I'm going to run this code. One of the things we can do, it has a bunch of, a corpus is a fancy name for a series of documents that you're going to use. So those would be a training set that you might care about. I'm going to go ahead and run this. So it has the Gutenberg collection. Punkt is one that you'll see. Reuters has a bunch of news articles. And you can see it's downloading all of these. I printed out in the Gutenberg collection. It has a lot of classic literature. It has Shakespeare, etc. And you can see some of the, I printed out just the beginnings of some of these documents. Okay, now I've actually uploaded these files, so now we can run this. So we can also just read files, read from our training data, if you will, from any text file. So I've uploaded the Bible text, and this is just previewing what's in there. It shows you how many characters there are, so it kind of gives you a general idea for the size. This is one of my favorites, the screenplay for the Fargo movie. If you haven't seen that, the Coen brothers, very, very funny. And you'll see some kind of fun n-grams that come out of this training corpus. Here we have the text from Hamlet. So you've got access to a lot of really great training material, training text, just from these toolkits. So the first thing that happens in any natural language system is you have to parse the text into tokens. Now, a token is at the lowest level that the system can actually reason about. And at this point, we're really just looking at individual words. There's also, of course, punctuation, including exclamation marks, question marks, numbers, things like that. And when we get later in the course, we'll see how those things get handled. But for the moment, let's just think of tokenization as breaking out the text into a set of individual words. So here I'm looking at the Fargo script. I've read that into movie text, and there's over 21,000 different tokens or words. And you can see we looked at the preview here, but now we've just got this big long list of tokens or words. So the first interesting thing to do is look at, well, how often do different words show up? And if you look at the most common, it's not super interesting because you have such common words, the, a, I. Here's where I said Fargo gets interesting because Marge and Jerry are characters in the movie, so they show up pretty frequently, which I think is funny. Now we can also look at this in a plot. So it's kind of nice when you're using notebooks, you can easily do graphs like this, make this a little bit bigger, and you can kind of visually see the difference. So the article the far more often than anything else. Okay, now an n-gram. So an n-gram, n meaning a number, which could be 2 or 3 words that appear in sequence together in the text. First, we're going to run some code to generate the list of bigrams that are in this, and we're also going to look at the PMI scores. So this is kind of comparing, well, how often do these two words show up together, but excluding just random chance, meaning that how much actual information do we believe there is when you see these words together. So let's run this cell. And in our Fargo text, you can see these are the bigrams that we see. Well, this is just the first list. So the very first bigram is just the word Fargo and A. So now you can, if you read the column going down, you see a screenplay by, but we would slide the window every time, and that would capture every bigram that shows up in that actual collection. I've got this helper function to process all of the bigrams and kind of come up with a better kind of view of it. So now we can look at the frequency and the bigrams and kind of normalize it and look at the frequency score. So that's what we're doing here. Marge, yeah, is number 10. There's some good stuff in here. Now here's a better look at the statistically significant bigrams using the PMI metric. So North Dakota, not surprising because Fargo is located in North Dakota. Personal matters, that's an interesting one. Paul Bunyan. So this gives you there's a little more semantic meaning here as opposed to just pure statistics, but kind of interesting to see. Gives you a sense again of the document, and we'll see how this is used later on. So we can do the same thing for trigrams, which would be 3 consecutive words in a row. Interesting, executive sales manager first shows up. Fence post stretches. If you recall, fence posts was actually, let's see, oh yeah, it was a little bit further down on the list of bigrams, but it shows up as more important here when we get into trigrams. So you get a lot more information, right? From trigrams, it's going to take up a little more memory, but these days that's probably not so much of an issue, but there's a lot of value in looking at trigrams as opposed to bigrams. And here, if we run this cell, we'll get a look at when we combine both trigrams and bigrams, we can see which are the most semantically relevant. And just by the nature of them being 3 words, I think you get more information. And so in this top list, we're getting all of the top ones are trigrams, not surprisingly, by a good order of magnitude. Now, some actual use cases for this. How is this useful? I mentioned spell checkers. So if you follow this example, I went to see, S-E-A, the movie. So that pattern would likely not show up very much in the training corpus because it's grammatically incorrect. It's really a typo. And so just by using these bigram, trigram analysis is a good way to identify, okay, that word is probably misspelled. Not only can we do spell check correction, but we can also figure out what word might probably be coming next. So as a suggestion, or really we're going to look at in more detail later in autocomplete, what I'm doing here is over the entire movie corpus, I'm taking the word A, and then let's say that the word tail comes next. So what this is doing is looking at the bigrams and figuring out, well, what might actually be meant. Now it turns out that when you have A blank, the word table in this particular training data, right, comes up most frequently. So it might suggest that did you mean table instead of tail? Now that's not a spell check, but that's kind of an additional use case that we can look at. Here we can use autocomplete, and if we run this, if you type the, same thing, like how often has it seen these particular words, so we can suggest what would come next. You can see this when you do a Google search. Google search has been doing that for quite a long time, right? That's actually a common SEO technique. And here, let's do autocomplete using trigrams. So now we're going to base it not just on 1 word, but 2 words. So at the, and we can see at the end would come up next. So this could be suggestions that would be given to the user if they're typing this out. If we take this even further, we can actually build a very simple rudimentary chatbot using this technique. So that's what this code here is going to do. I'm going to go ahead and run this. And there's a couple of things to consider here. So every time you have a context, so some set of words, you're going to generate the next one. You can generate the probability of every word in the vocabulary that might come next. In the case of bigrams and trigrams, not every word you know is going to show up. There's going to be some that have 0 occurrences. But you also want to limit to kind of the most likely. So these top K and top P. So top K would mean only take the 5 most likely words in terms of number of occurrences that would follow that context. Optionally, you can say top P would be 0.9 would be take words that add up until you get to a cumulative probability of 90%. and then stop considering them. But there's one other aspect to this, and that is that you want to add some amount of randomness to this. If you always take the most likely word, you're not going to get a very interesting chatbot. And it turns out the quality of AI tools in general, randomization helps increase the quality. So what is this going to do? If there are no candidates, it's going to find a fallback, meaning that if I've never seen this sequence of words before, I have to pick something. But first, what it's going to do then is calculate all of the probabilities. By the way, a full transformer like ChatGPT, these basic concepts and logic are going to be similar. So what's the probability that every word I know might follow, or in this case, every possible word? Okay, now sort it by probability. And then what we're going to do is we're going to do sampling. So apply that top K and top P logic. So basically, if I've got 100 possible words that might come next, but top K is only 10, I'm going to drop the last 90 and only consider those 10. And then essentially, I'm going to do that random sampling using those weighted probabilities and pick my next word. So here, this run mini AI chatbot is a method I've got here. And so the president flies on Air Force blank. So let's run that. And so here you can see the president flies on, okay, so it generated Air Force One, which we would expect. And then you can see our chatbot's not very good because it switched to one night, which might make sense in a different sentence or a different context. President flies on Air Force one night, the man in. So our chatbot's not doing very good, but that's because this is an extremely simple model. Now, the fact that our bigrams and trigrams don't capture every possible word, and this is a small training corpus, so we're obviously going to be missing some things, but another technique you can do is smoothing or different forms of interpolation, meaning that even words that you haven't seen necessarily in that context, you can give a small probability that they might show up. And also, you kind of leveling the playing field in a sense. So here's an implementation that does some interpolation, and this gives us a little bit more of an interesting result. It's missing some punctuation, but nonetheless, I've also added the probabilities here. So we're starting with the president boarded air. And here you can see the probabilities. So Air Force, that was by far the most probable, almost a 46%. And so it did select 4. So the president boarded Air Force, and then 1 is extremely likely because it almost always sees Air Force One. Not many other words follow that pattern apparently, or it's just in our training corpus. So it did select that. Now it gets more interesting. So here you can see before we picked night, and we got that. It was a 20% probability, but we happened to get it. Here we also selected night. Okay, so the president boarded Air Force one night. And then here you can see, now in this case, we did not select the most likely. Granted, 9% is not much more than 8%, but the president boarded Air Force One night. And here, I saw him in the, okay, well, I only told it to generate 10 tokens. So we're starting to get some things that look a little bit better now, a little bit more like maybe what you would see. There's a grammatical error here, obviously, but so there are techniques that you can do to improve kind of just the basic n-grams. So this has been just a quick tour of kind of what n-grams are. These are the first kind of statistical technique that we're going to look at. There are other ones that we'll follow up with in subsequent videos. So hope that was interesting, and I'll see you in the next video. Thanks.